Bismillahirrahmanirrahim. Assalamu alaikum. Hi everyone. My name is Yasmin Tahir Radauna. I am pleased to present to you a presentation on polymer gel dosimeter. I hope to add to you some useful information on this subject. Overview about the subject. Polymer gel dosimetry is a radiation dosimetry technique using specialized gel materials to measure absorbed radiation dose. Gel contains chemicals that undergo polymerization upon exposure to ionizing radiation, resulting in property changes. Alternation in gel properties post-radiation exposure can be quantified to determine the absorbed radiation dose, providing 3D spatial resolution of radiation dose. Polymer gel dosimeters offer high spatial resolution, making them available in radiation therapy, protection, and medical imaging. Polymer gel dosimeters offer challenges such as gel instability, preparation, reproducibility, and calibration complexity, hinder standardization and clinical implementation. What is the working principle of a polymer gel dosimeter? Polymer gel dosimeters are materials used to measure and quantify absorbed dose of radiation, commonly used in medical dosimetry for radiation therapy or in radiation protection. The working principle behind polymer gel dosimeters involve the chemical changes that occur within the gel when exposed to ionizing radiation. Here is a simplified explanation of their working principle. We can summarize working principle of polymer gel dosimeter in this form: gel preparation, irradiation, scanning, analyzing, and then gel dosimetry. Explain this point in next slide. Here is a simplified explanation of their working principle. The previous form was summarized in the form of points that can be explained as follows. Gel preparation. The dosimeter gel is prepared by mixing various components such as monomer, vinyl monomer like acrylic acid, a cross-linker which helps in polymerization, and sensitizing agents to enhance the gel sensitivity to radiation with a gelatin base. Irradiation. The prepared gel dosimeter is exposed to ionizing radiation such as X-rays, gamma rays, or other source of ionizing radiation. Polymerization. When the gel is exposed to radiation, the energy from the radiation interacts with the components of the gel, causing polymerization or chemical changes within the gel. Dose-dependent changes. Absorbed radiation leads to change in chemical structure or physical properties of the gel, such as change in its optical density, proton relaxation rates, or magnetic resonance properties. These changes are directly related to the absorbed radiation dose. Then continue analysis. The dosimeter is then analyzed using techniques such as magnetic resonance imaging, optical CT scanning, or other appropriate method. This technique helps visualize and quantify the change within the gel due to the absorbed radiation. Dosimetry calculation. The measured changes in the gel are correlated with a calibration curve or mathematical models established through prior calibration experiments. This correlation allows for the determination of the absorbed radiation dose based on the observed change in the dosimeter.
Assalamualaikum and hi, my name is Muhammad Zulkarnain Ruslan. For the next part is dosimetric properties. The dosimetric properties refer to the characteristic of a dosimeter that determine its ability to measure radiation dose accurately and precisely. There are 7 dosimetric properties in polymer gel dosimeter, including stability, linearity, reproducibility, tissue equivalent, spatial resolution, sensitivity, and energy dependence. The stability is the ability of the gel dosimeter to preserve its dose response over time without significant diffusion, fading, or degradation. Stability is important for accurate and reliable dose measurement. Next is linearity is the degree to which the gel dosimeter's dose response is proportional to the absorbed dose. Linearity is desirable for a wide range of dose measurement and easy calibration of the gel. Next, the reproducibility is the consistency of the gel dosimeter's dose response under the same or similar conditions of irradiation and readout. Reproducibility is essential for minimizing the uncertainty and variability of the gel measurement. Next, for the tissue equivalent is the similarity of the gel dosimeter's physical and radiological properties to those of human tissue. Tissue equivalent can be affected by the composition and the density of the gel as well as the type and energy of the radiation. Tissue equivalent can be assessed by comparing the physical density, effective atomic number, relative electron density, CT number, and elemental composition of the gel dosimeter. Next, for spatial resolution, the spatial resolution is the smallest distance that can be resolved by the gel dosimeter. This can be influenced by the size and the shape of the gel container, the readout technique, and the image processing method. Spatial resolution is important for capturing the fine details and gradient of the dose distribution, especially in complex or conformal radiation field. For the sensitivity or dose response, the dose response depends on the various factors such as the type of gel component, the readout technique, and the post-irradiation condition. For instance, a linear dose response of Normonics gel dosimeter can up to 26 gray using MRI, while using CT can up to 40 gray. Lastly, for the dose rate or energy dependence, these are the effects of the radiation dose rate and energy on the gel dosimeter's dose response. Ideally, the gel dosimeter should be independent of the dose rate and energy, meaning that its dose response should not change with different value of this parameter.